right, let's try this again. This is my second time doing this video because I accidentally deleted the last one before I saved it. I recorded the entire thing and hit like the undo button and boom, everything got deleted. I was so happy. So we're going to try this again, okay? Maybe this time I'll cut back on the rambling a little bit, but I don't know. I have a good time when I ramble. I think you guys do too. So I'm just going to ramble on, all right? Like Led Zeppelin said, ramble on. Okay, here we go. So what are we talking about today? Have you ever heard that song? Good song. I'm talking about similar figures, all right? So chapter 8 is all about similar figures, similar shapes, all right? Then also setting up ratios and proportions, okay? That's what this chapter is all about. Solving proportions is huge. It's going to help us tremendously when we get to chapter 9. Okay, so it's important that you understand how to set up a proportion, number one, and then once your proportion is set up, how to solve it. Okay, how to solve it. All right, but today we're going to talk about characteristics of actual similar polygons or similar figures, similar shapes, and also talk about their the ratio of the perimeter and area of similar polygons and shapes. What makes polygons similar? Okay, so when we're talking about similarity, we're usually talking about, one shape is big to small, and you don't need to write much down from this. I would just write the title and the objective for today from this slide, all right? Because we're going to talk about how to form similar polygons. So similar polygons are formed in two different ways. There can be a dilation or an enlargement. A dilation or enlargement, when we talked about transformations back in chapter 4, I think it was, in first semester, we talked about dilation or enlargement when our scale factor was greater than 1. Another real-life example of a dilation is a film projector. If you're going to the movies, and you're watching a movie, what you're watching is a projection from a tiny projector, okay? From a projector that's, this big or something, or this big. I don't know how big they are, but it's projecting onto a huge screen. That would be a dilation. That would be an enlargement because it starts off as a really small, like in the actual projector, it's really small picture, and then it becomes larger. All right. I have a projector too. My projector is legitimately about just a little bit bigger than this, about this big. Okay. And it makes a projection onto my wall. It's a good projector. It's pretty solid. I like it. Great for Sundays, for watching some football or watching a movie and watching a game up top. Maybe there's, I don't know what sport is on, but I can watch a movie too. It's actually pretty fun. So here I go rambling on again. All right, let's keep going. Dilation, I'll make one more connection. If you go to the doctor or eye doctor specifically, and you have your pupils dilated, so they can inspect your eye a little bit more. I don't know how many you have had that. I usually get it, once every year, just to check on my eyes. Maybe once every other year, I can't remember. But your pupils become huge. All right, and your pupil basically encompasses all of your cornea, and your cornea is what makes your cornea, like I forget what it's called, like the cornea rings is what makes your eye, blue, brown, what have you, hazelnut, green, magenta, whatever color it may be. That's what makes your eyes. But when you have a dilation, whatever. Let's go to reduction. Reduction is like shrinking. Okay, a reduction is a shrinking when your scale factor is less than 1. Taking a picture. I can take my phone, take a picture on my phone, and instantaneously put it out there on the line. So when you do that, what you're doing is you're taking a reduction of that snapshot. Boom, I take a nice little picture and instantaneously put it out there on the line. That is actually we're looking at similar polygons there. All right, you're looking at similar polygons. I'm reducing what I see there in front of my face to instantaneously put it out there on the line onto Instagrams or onto Snapchat or onto TikTok or Twitter or Facebook, whatever you may use. But I'm sitting there taking a picture, instantaneously putting it out there on the line, or sharing it with my friends, sending a picture to my friends instantaneously on the line. All right, so here's what makes similar polygons actually similar. Here's how we know. All right, the first characteristic that they have to have is the ratio of the measures of their corresponding sides are equal, and we'll talk about what that means, or more about what that means in the next slide. and their corresponding angles are congruent. So again, if I'm you, I'm taking notes at home, I would make sure to write those facts down and these two as well. Okay. Make sure you get all that down. All right. The ratio and the measure of the corresponding sides are equal and the corresponding angles are congruent. That's what makes similar polygons similar. So you don't need to write this down. I just would look at this. I would actually write this example down the bottom left. Okay. We have two, it would be triangle ABC is similar to triangle EFD. And I would try to draw the picture just like this. Because when two shapes are similar, they don't have to be oriented the same way. These two rectangles, these two shapes are oriented in the same way. These two are obviously not. ABC looks like it's rotated a little bit. In order for two shapes to be similar, they have to be the same shape. Here we have a pentagon, two pentagons, two rectangles, two triangles. These two shapes are not similar, okay? Are not similar. Why? That's what that mark means. How do we mark similarity? I forgot to say this. When you're writing down your notes, here, this little squiggle means similar. All right. We talked about how the squiggle with the two equal signs, or with the over the equal, that means congruent. You've seen this, that means about. Well, just one means similar. So along those same lines, a squiggle with a line through it just means not. These two shapes cannot be similar because we're comparing an octagon to a hexagon. Two different shapes, no similarity. All right, so let's look at an example here. So I said that the ratio of the corresponding sides must be congruent. So I want to find the missing side lengths here. I want to find my missing side lengths. First side length I want to find, let's call this X. We'll find KL. So what I want to do is I want to use two sides that I already have, set up the ratio of those two sides to help me find sides that I don't have. I know that AB, first two letters, is 15. JK corresponds with JK, because that's the first two letters, and that's 6. Now, obviously, these are oriented pretty much the same way. They could be rotated, so that's why I want to emphasize the order in which the letters appear. AB is the first two, JK is the first two. All right? So I can set up a ratio using those two sides, 15 over 6. Okay, I go from left to right, big to small. Important the order in which I do that. So if I want to find X, well, I know KL is our letters 2 and 3. So BC, which are letters 2 and 3, corresponds with that side. Okay. So again, important in the order in which I write this is important. I need to write 20 over X. I'm going from big to small, big to small. I could have also written it as 15 over 20 equals 6 over X. I could do that, okay? But for the sake of this problem, I'm just going to go left to right over left to right. And from here, we cross multiply and solve. All right, this is called a proportion. This is what we're going to be setting up. Proportion is when a fraction is equal to a fraction, or in better terms, when you set two ratios equal to each other. All right. To solve this proportion, I want to cross multiply. So I'm going to do 15 times X. So 15X equals 20 times 6, so 120. So X. Hold on. I say 6. X is not 6. I was thinking of a later problem. I apologize. Just confused myself there. So this is 8. All right, now I'm going to find another side. I'll call it CD. We'll call it Y here. Okay. I want to figure out, okay, what corresponds with Y? Well, CD is the last two letters. LM are the last two letters. CD corresponds with LM. So I'm going to set up a ratio of those two. Y over 10. Now, what I set them equal to, I can use 15 over X, or I can also use 20 over 8, because both of those those are both ratios of corresponding sides. I'm just going to stay consistent and do it 15 over X. It's just a little bit easier that way for some people to understand. You can also have done 20 over 8. But again, we have a proportion set up here. Let's cross multiply. I have 6y equals 150. So y is 25. Now I can find L or JM, excuse me, but I'm just going to stop there for now. Another way we could have done this and is recognized, what the actual ratio was. 15/6 is really, if I reduce those both by 3, that's 5/2. And I could have just used that to figure out what JM is, or I can figure out what Y is using that as well. All right, but that's something we'll talk about later. Okay, so let's talk about a word problem. Okay, you can actually do this. You can stand next to a tree and do this and measure your shadow. I know you're all going to go outside and do this later on for sure. A tree is 25 meters tall, so I'm going to label that tree. Boom, 25. Cast a shadow that is 32 meters, so I'm going to label the shadow 32. Okay, Abby is standing near a tree. She is 1.6 meters tall, so I'm going to label Abby 1.6. How long is her shadow? So right here, I'll call that X. Again, anytime you're doing a word problem like this, I would make sure to draw a picture. Whether it's just 2 triangles or whether you go full on and draw a tree and draw a person. All right. So I see that I have 25 and 32 go together because it's the tree and shadow. And then I have 1.6 and X go together because it has everything to do with Abby. All right. Now I could draw these 2 separate, or I could draw them, I could have drawn this little red triangle separately from the tree triangle. Doesn't matter. But let's set a proportion. That's our goal. Set a proportion. 25 and 32 go together, so I'll keep 25 and 32 together. 1.6 and X go together, so I'll keep 1.6 and X. Now, I can set this up in multiple ways. That's why I'm giving myself some space to do that. That works. I also told you on the last slide to go big to small, big to small. So I'll go big, which is 25, to small, which is Abby. Shadows together. Shadow of the 25, shadow of the tree, over Abby's shadow. You can do it like that. Okay. I could set up another way. I could go X over 1. I could flip this. X over 1.6 equals 32 over 25. Same thing here. 1.6 over 25 equals X over 32. I can do that. No matter what, everyone, we will be cross multiplying, and we will still have 25X equals some number equals 51.2. No matter what. When I'm doing these word problems, I like to keep like tree together, tree with tree shadow, person with person shadow. It just helps me a lot. And if I divide this, you get 2.048. All right, that's how long her shadow is. Let's look at one more example. Let's talk about the ratio of their sides. AB goes with EF, 4/6. AD, buckets, what just happened? AD, E 1 to 4 goes with 1 to 4, E to H. So I got 2 over X. Now you can think about 4/6, how does that reduce? 4/6 reduces to 2/3. So even before doing this work, I know that X has to be 3. All right, 4/6 is 2/3, then this has to be 2/3. I can also cross multiply and solve this. 4X equals 12. Oh, look, just to be sure, X is 3. That actually works. Okay. Remember, the ratio of the corresponding sides must be equal. All right. 4/6, I can reduce that to 2/3. Well, then this has to be 3. Also, the corresponding angles are congruent. So I have 50 is angle A. Well, what corresponds with angle A? Angle E. So Y must equal 50 degrees. Again, I'm going to say this. These two are oriented the same way. All right. If they weren't, you have to pay attention to the order of your letters. Okay. So these next 2 theorems here, we're talking about the perimeter of similar polygons and the area of similar polygons. The perimeter of 2 similar polygons is just equal or perimeter, the ratio of the, let me tell this again. The ratio of the perimeters is equal to the ratio of the corresponding side lengths, okay? We'll talk about that in the next slide. Let's discuss area. The ratio of the area is a little bit different. So if I have two polygons, the ratio of those two polygons' area is equal to the ratio of their sides, but squared. The sides will be squared. Okay. The ratio of the sides squared, which to me actually makes sense, because when you're talking about area, how do you measure area? You measure area in square units. It only makes sense that to talk about the ratio of areas, that I have to square the sides. Okay, well, that's really what you're doing when you're finding the area of a shape. I'm multiplying two sides together, or something like that, which we'll talk about in chapter later on, chapter 11. But really, that's what you're doing. So I might as well square the sides here. So how does that apply? How does that look? What do I mean by all this? So let's look at an example. RST, the area of RST is 75, and I want to find the area of PQT. All right, well, I know that RST is 75, so I'm going to take that as the area of my first shape. I don't know the area of my second shape, so I'm going to call that X. Which side corresponds with the 75? Well, which side is from RST? Here is RST right here, so that 10 goes with it. All right, the 75 and the 10 come from the same shape. The X, which is what we're trying to find, and the 14 come from our other triangle. All right? And these two sides, their ratio is going to be squared. So, oh, look at that, it's already here. So, if I go to the next page, work. It's probably already there because I already made this video, obviously. Duh. Okay. Making it for a second time. Hopefully the second time is better. We'll see. So, as I do this work, I need to remember, okay, let's talk 75 over X, that's not going to change. What I'm doing here, when I square these sides, I have to square the numerator and the denominator individually. I'm going to do them both. So 10 squared is 100, 14 squared is 196. I need to square the top and the bottom. I need to do both of them. I can't just square the 10. It's not going to be fair to the 14. I have to square both. After you square them, it's just a proportion here. Again, this whole chapter is all about solving proportions. Cross multiply. 100 x equals 14,700. Divide by 100, I get 147 is my area. Boom. That's the area. I could say meters squared. Since it was 14 meters squared. All right, so his last problem talks about perimeter, right? The perimeter ratio of perimeters. So it says if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding sides. All right, so let's look at our example. I have an example about Shia LaBeouf and his garden. Shia LaBeouf too decided their largest garden. All right, it was a rectangular garden. Okay, well, it was 6 by 15. All right, his new garden, he wants the length of the new garden to be 35 feet. Okay, find the perimeter of the original to the enlarged one. Well, what's the perimeter of the original garden? The perimeter of this garden here, well, if that's 15 down here, then I got a 15 up here, and I got a 6. So the perimeter is 42. How do I know that's 15, 15, 6, and 6? Because it's a rectangle. It's a rectangle. All right? So rectangles, remember, the opposite sides are going to be congruent. Okay, so my perimeter is 42. Here, I don't know the perimeter of the new garden. That's what I'm trying to find. So automatically, I know I have a ratio of their perimeters, the old versus the new. Okay, the X should be red. I'll make that X red because it comes from my enlarged garden. All right, well, I want to find two sides that are corresponding. The two corresponding sides are the 15 and the 35. So I'm going to go equals 15 over 35. 42 and the 15 go together. X and the 35 go together. Let's cross multiply and solve. 15x equals 1470, maybe. Yeah, would you look at that? I remember from the last one. And then x is, if I do 1470 divided by 15, I get 90 feet. That's the perimeter of his new garden. I could ask you, okay, if the perimeter of the new garden is 98 feet, what's the width? Well, if this is 35 and this is 35, all right, so that must be 70. Well, then I have 18 left over. It must be 9 and 9. Now you would know the new dimensions too. Okay, I can get a lot of information from this. This is a in real life example. Like if you wanted to enlarge a garden, you could actually do this. I don't know how many of you are going to do this. Maybe later on in your life, maybe if when you grow up, you want a garden. You want a garden. You maybe try to build one. Hey, let's do it. Let's build it. Let's remember what Mr. McConey said back in the day, back in chapter 8. We were talking about similar polygons, but that's it. Again, if you have any questions on this, setting up proportions, solving proportions is important. It's going to come back a lot in this chapter, so make sure you get those questions answered. Hopefully, I won't delete this recording. Let's see.